All right, so now that we've actually dusted off some of our cobwebs and we again remember all of the cool things that we love about the merge sort, let's actually jump back into some of the technical bits. That is, let's chat about the overall running time of the merge sort. So by overall running time of this thing, what I mean is I want to go back to some of these examples and begin to count the number of comparisons that this process is going to take to actually go through and sort something. So our end goal is to have some nice little function that's going to look like t of n. So the n here is going to be the length of the list that we're going to feed into it. And then what's going to kick back on the output side is it's going to be the number of overall comparisons that are going to happen. So to help us out, we'll look at some of these nice tiny little examples. So we'll look at a list of length 2, we'll inflate this up to looking at a list of length 4, then we'll look at something that's maybe of length 8. And after that, we'll have a pretty good feel and kind of a really confident way that we can say, okay, from these examples, it appears that this is actually happening. And from that, we can make a really nice guess as to the overall running time. And then we'll jump back and actually show that that is exactly the running time we're hoping to see. So it's kind of this nice layered approach as we do a few examples, get a kind of a nice feel for what's happening. We get this kind of nice recursively defined function that's going to emerge afterwards and then kind of build things from there. Okay, so let's jump into this nice little toy example. So what I have here is I'm going to have this massive list that has all of 2 things in it. Those 2 things happen to be the very first 2 numbers in Jenny's phone number. So I have 8 and 6. As you already saw, we're going to have the next example be the 8 and the 6 and the 7 and the 5. And my goal is to run through this merge sort and then count the number of comparisons that are going to occur. So the way that merge sort is going to attack 8 and 6 is that it's going to see that list and it's going to have more than one thing in it. So what has to happen is that it's got to be ripped in half. So I'm going to have a list that's got the 8. It's going to have a list that's going to have the 6. What ends up happening there is that both of those lists are going to have length 1, so I know that I can invoke this secondary process of actually sewing these things together. So here's where I'm going to invoke that nice little merge function. So the way the merge function is going to process this is that it's going to grab that first element from the first list, so the 8, and then it's going to grab the first element from the second list, or the 6, and it's going to compare those 2 things together. You can see that the 6 is obviously going to win because I'm organizing these things from smallest to largest. So what's going to happen is that I'm going to remove that thing from that that second list, and I'm going to paste it down into this newly constructed list on the bottom. Then what's going to happen is we're going to go back to those 2 little lists. I'm going to again still be looking at the 8 from that first list, but now I'm going to see that that second list actually doesn't have anything in it. So the comparison is kind of dumb because it doesn't really happen. And then I'm just going to take the 8, and the 8's going to be removed from this list, and voila, it gets pasted at the very end. So formally, we're actually having 2 comparisons that are actually going to occur, even though that second one is kind of dumb. There's one really good honest-to-goodness comparison, and then we go back to that, and we see that we really only have an 8 left, so then the 8 gets plopped in as that second bin. And voila, we have 2 overall comparisons. So for list of length 2, the number of comparisons is then going to be a 2. All right, so let's up the ante just a little bit. So here we have this nice little list that's going to have 4 things in it. So I have 8, 6, 7, 5. So we're chopping off the 309. And again, we're going to walk through the steps of this merge sort and again, trying to count the number of comparisons that are going to occur. So the very first thing that needs to happen is, obviously I have this list of length 4. It gets ripped in half. So now I have 2 lists, each of which are length 2. And then we have this recursion that's going to happen again, in that I'm going to take those 2 little lists of length 2 and they're going to be having to be ripped in half again. And finally, I'm at this stage where I have all of these nice little lists that are all of length 1. And now is when we begin to sew all of these things back together. So what's going to happen is I have that 8 and 6 again. Well, we already know how to sort those things. So the 6 is going to go into the first bin, the 8 is going to go into the second bin. So I have 2 comparisons that have happened so far. Next up, I'm going to have the 7 and the 5. The 5's going to win, and then the 7's going to trail afterwards. So it's very similar to how the 8 and the 6 ended up going. So we get another 2 comparisons. So in total, on this row, I had 4 overall comparisons. So I had 2 from the first bin, 2 from the second bin, multiply those 2 numbers together, and voila, you have 4 overall comparisons, which is going to be key. Is you're going to see this nice little binary structure emerge, and goodies are going to follow out of that afterwards. Okay, so now that we have these 2 little lists, each of length 2, we're again going to be sewing these things back together. So here's where we actually got some kind of interesting things in the merge operation, in that I'm going to be looking at that very first list, grabbing the first entry, which is the 6, I'm going to look at the second list, grab the very first entry, which is the 5, do the comparison, see that the 5 is going to win, so it's going to be plopped down into that new list down below, and that 5 is essentially going to be chopped off. Okay, so then we go back up. We're still holding on to that 6, and now we're going to compare the 6 to the 7. Well, here you can now see that the 6 is going to win because 6 is smaller than 7, so the 6 gets chopped off, and it's going to go down here. And then we go back up to the top, and now we're going to be comparing the 8 with the 7. We can see that the 7 is going to win because it's smaller than the 8. And now we got this kind of last dumb comparison that's got the 8 compared against nothing. So hooray, the 8 wins because it was the largest one. So it gets placed into that last little bin, and voila, we have our perfectly sorted list of 5, 6, 7, 8, and everybody's really happy. What happens here is that you can see that there was another 4 comparisons that were going to take hold. So we had 2 in the first, or we had 2 versions of 2 in that middle row, giving us 4 comparisons. Now we're going to have another 4 comparisons. So if I add those 2 things together, I'm going to get 8 comparisons. So over here I have a little bit of scratch work that's actually going to help us kind of see the general pattern. What's going to happen here is that when I had these 2 little groups of singletons, what ended up happening is that I had 2 and 2, which gave me the 4. Here I have one group where we had all of this stuff merge into that final 4. So what's going to happen is that I'm going to have at some point in time some process that's going to count the number of comparisons up to that blue squiggle line, and then I'm going to have to add on the number of comparisons at the very end. The number of comparisons in that very last step is always just going to be equal to the length of the original list. At some point in time, I have to end up with that list, so I'm going to have to cycle through all of those things to kind of properly put them into their final bins. So I'm going to have up to that stage a number of comparisons, and then at the very end, I'm going to add on an n, and then I'm going to be happy. So here adding on the n was just adding on a 4. So the total number was 4 plus 4, which is 8. One of the ways we're going to want to view this 8 is by viewing the 4 plus 4 actually as a 4 times 2. So that guy right there. And the reason for that is that it's always beneficial to see the number n emerge in your final formula. So that little n is the 4 because it's the length of that list that we were playing with. So that's going to make an appearance in this formula. So all things are great at that point. The other thing that we're going to see is we're going to see the 2. The 2 is actually going to be emerging from that little exponent right there. And if you go back to the last example, we actually had that same exact structure emerge as well. I had this 2, which was my n value, and then officially it's multiplied by the exponent that's going to emerge, which is that little 1, which is cool and neat, which also makes a lot of sense because what's happening is that as I chop this thing in half over and over and over and over again, I get a feel for how many rows are going to be in play as I begin this back substitution. It's essentially going to be connected to the exponent that's in play. Because if I had 4 overall things and then I chopped it in half, then I went down to 2 groups of 2, and then I chopped each of those in half, giving me 4 groups of 1. So it makes sense that I'm going to have some 2 that's going to enter the picture somewhere. And that's exactly where that 2 is coming from. It's that exponent on the 4 that we're looking at. So let's up the ante one more time until we can kind of see the general formula take shape. And then I'll give it a good pause, and then we'll come back and actually show why this all works, kind of really digging into the technical bits. Okay, so here I've thrown away all of my numbers because I got sick of writing 8, 6, 7, 5, 3, 0, 9. Also, that only has 7 things in it, so I'd have to add on some extra dumb number, and I just didn't feel like doing it, so I'm just going to show you the kind of general blank structure of what's going on here. So every single merge sort that's going to start with a list of length 8 is going to follow this exact same pattern. Maybe the crisscrossies are going to be a little bit different, but it's essentially going to do that. So the way that this is going to be unfolded is that I'm going to start with a list of length 8. It's got to be chopped in half, giving me 2 lists of length 4. Each of those lists of length 4 have to be chopped in half again, giving me 4 lists of length 2. And then those lists of length 2 all get chopped in half again, so now voila, I'm sitting with 8 little singletons and everything is great. Once we get down to the singleton stage, we now know that we enter stage 2 of this process. Now we begin this merging process. We're going to begin kind of zipping these things all together, and hooray, everything was nicely sorted. So what's going to happen is that when I have these 8 little singletons, I'm grouping them into blocks of 2. So each of those are going to have 2 comparisons. So in total, I'm going to have 4 of those, each of which are going to have 2 comparisons. So I have 8 comparisons at that row. The next bit's going to have, okay, I went from 2 blocks of 2, or 4 blocks of 2, I should say, down into 2 blocks of 4. So what I'm going to have is that if I'm looking at that guy and if I'm looking at that guy, I'm going to have 4 overall comparisons to get down there. It's essentially the exact same as the last step here. And the same thing is going to happen over here, is that I had 2 blocks of 2 going down into 1 block of 4, so another 4 comparisons. So each of those had 4 comparisons, and I had 2 of them in total. So again, I have a 4 times a 2, or 8 total comparisons in that row. And then that very last step is again going to be this process of how do I take those 2 blocks of 4 and then zip them all together into 1 block of 8. So again, that's going to take 8 overall comparisons, which is always going to be equal to the n value that we have in play. That's going to always happen is because at the end of the day, I need a list that's going to have length n. So I got to merge all those things together and everything is awesome. So I get another 8, which is key. You can see that each of those rows ended up having 8 overall comparisons, and the number of rows was exactly equal to the exponent that we saw on the 2. That's going to be the other key thing, is that we're always going to have the 8 emerging, and then it's going to be multiplied by the exponent that emerges afterwards. So that exponent, again, has this really special shape in that we have this logarithmic design for it, in that if I'm looking at 2 cubed, if I want an operator that's going to rip off the exponent, then I have a logarithm. So if I have log base 2 of 8, well, 8's the same thing as 2 cubed, so that's going to rip off the exponent 3. So the number of steps that this process took was then going to be 8 multiplied by 3, or log base 2 of 8. So what we're kind of leaning towards thinking is that it appears that the number of comparisons is somewhere along the lines of an n multiplied by log base 2 of n, which is pretty cute. You get this kind of nice little bound for what's actually happening. So the n kind of makes sense because each of those rows are going to have n comparisons, and then the number of rows is going to be that exponent, that kind of as we chop things up as we go. So it's this really nice and tidy way to kind of see this pretty general formula take shape. It's got really nice properties, so it's going to be optimal when it comes to doing these sortings via some comparisons, and that we can't actually do any better than n log base 2 of n. We're going to look at a couple other examples to kind of see some things that are going to have some comparisons to this, but this is really about as good as it's going to get. So it's this cool way to sort some things. We know that we're going to have to pass things around a few times, and if we can have things over and over and over, we're going to see some logarithms emerge. So hopefully that looks really similar to when we were doing some of these things with these Turing machines, is that we wanted to try to basically parse through this thing a bit more efficiently. So rather than having to go through, n squared or something terrible like that, I'm going to read across this thing over and over and over again. But if the number of times I can read across this thing can be reduced, I don't see an n squared. In fact, I get an n log base 2 of n. If I just went classic old school selection sort and all of those ones, then I'd have an n squared, because the number of rows that would end up happening here would actually be the number n again, because I'm not really chunking things down as we go. So in the next video, we'll jump back and kind of really show where the recursion meets this formula, do a little bit of induction. So it'll be a good fan favorite to remind you of how that whole process works. And then we'll jump into the quick sort and kind of show all the differences between these two worlds.